a colorful new design tool developed by MIT researchers allows individuals to create polarized light mosaics that can be printed on cellophane to make data visualizations, passive light displays, mechanical animations, fashion accessories, educational science and design tools, and more. Tisha Melody Sidapkadi, a PhD student at MIT, is leading the use of regenerated cellulose to make what she calls Polagons, machine-made color-changing mosaics that use polarized light to inform and delight. Such polarized light mosaics have previously been crafted by hand, and the researcher was inspired by artists such as Austin Wood Kamara, whose innovative Polagons art is based on the same physics principles. The new computational Polagon design system, however, enables a fabrication process based on laser cutting and welding, all with minimal assembly by the user. Users first import custom mosaic designs and the system computes the feasible color palette given a user's cellophane supply. Uploading multiple designs to the interface allows users to create mobbing mosaics that can transition from one image to another. Then it is on to logistics. Polagons optimizes the necessary constituent components for each scenario, like the type and number of seats needed. Once the user finishes uploading designs, playing around with colors and visualizing the color changing behaviors, they can export the fabrication files and chop them up in a laser cutter. What is so special about cellophane anyway? The sheets have a property called birefringence, meaning that when light passes through, the speed of light is different depending on the propagation angle. When the sheets get put into a sandwich of two polarizers, that is material that only lets certain polarities of light pass through while blocking others, they appear colored. The colors you see depend on different factors in the material, like thickness and the angle of the material relative to the two polarizers. To create that color changing effect, you just need to rotate the image or the polarizers, because then you are changing the angle of light propagation. Perhaps in the future, since these designs are non-electronic, they could enable interesting underwater applications where you put these types of mosaics in places that might be difficult for electronics to stay in. That is what's special here, that all of these color changing effects are mechanical, says the researcher. One limitation of Polagons is the inability to represent every color on the rainbow in a continuous way. The team believes a potential solution could be changing the fabrication process to support a constant mode of building colors. This might mean 3D printing a birefringent material to access a more extensive palette and have more control over the colors.